Hi all, welcome to new session of Wireless and Mobile Communication Lab session. I am Anush GR from the Department of Electronics and Communication, New Horizon College of Engineering. So in our first session, we had considered Okumare model. We had implemented the Okumare model using MATLAB. Now the next experiment which we are considering is the Hata model. Now, as you have seen in case of Okumare model, we had to use the Okumare curves to find out the value for AMU and G area. So every time you change your frequency, you had to find the corresponding value for AMU and G area because AMU and G area both dependent on the frequency, and AMU alone depended only on frequency and the distance of separation between the receiving and transmitting antenna. So writing a generic program would have been difficult. What did Hata do? Hata introduced an equation and he made it completely mathematical. It did not have any graphical graphs to be used to find any value. Nothing of that sort was required. Hata model represented the urban area propagation loss as a standard formula and supplied correction equation for application to other situation. That is what equation he first laid was for urban area. Then he extended the same equation by taking some correction factor and extended it to suburban area and small cities. We will be seeing it further. He extended it. Okay. Now the model is valid for a frequency ranging between 150 megahertz to 1500 megahertz. And the formula to find out the path loss laid by Hata model is given by this L50 urban. Now this is the value only for the urban area. Okay, L50 urban in dB is 69.55 plus 26.16 log FC minus 13.82 log HTE, which is the height of your transmitting antenna, minus AHRE. Okay, we'll see what this factor is. Plus 44.9 minus 6.55 log HTE into log D. So this is the formula laid by your Hata. Now let us see what each of these terms are. FC, we know it is the frequency and it is given in megahertz. It is ranging between 150 megahertz to 1500 megahertz. HT is the effective transmitter antenna height and it should range between 30 meter to 200 meter. And HRE is the receiver antenna height and it is ranging between 1 meter to 10 meters. D is the separation distance between your receiving and transmitting antenna, and AHRE is the correction factor for effective mobile antenna height, which is a function of the size of the coverage area. We will see this. How do we calculate this? Now let us first see what is AHRE, how is it calculated. Now if for a small and medium sized city, the mobile antenna correction factor AHRE is given by this formula. That is 1.1 log FC minus zero point 0.7 into HRE minus 1.56 log FC minus zero point 0.8, and the value is in dB. This is the correction factor given by Hata for small and medium sized city. And it does not have any dependence. There is only one equation. For all frequency range, you can use the same equation for a small and medium sized city. Coming to the correction factor given by Hata for large cities, had two set of equations to be used. One, if the frequency under consideration was less than 300 megahertz, and other formula if the frequency was greater than 300 megahertz. So if the frequency is less than 300 megahertz, the formula to be used was AHRE was given by 8.29 of log 1.54 HRE the whole square minus 1.1 dB. Similarly, if your frequency was greater than 300 megahertz, the formula to be used was AHRE was equal to 3.2 into log 11.75 HRE the whole square minus 4.97 dB. So this was the correction mobile antenna correction factor given by Hata to be used in this equation. You can see AHRE was one of the factor which was unknown to us. So we can find it out using these formulas. It depended on what is the area under consideration. If it was a small and medium size city, we will go for this formula. If it was a large size city, we have to consider what is the frequency. If it is less than 300, we will go for the first formula, this formula. If it is greater than 300, we will go for the second formula. Okay, I hope you have a clarity into this. Now let us move forward. Let us see what did he further suggest. To obtain path loss in suburban, as we found out initially, we saw the formula was given for urban area. The formula given by your Hata was for urban area. Now, if we have to find out what is the path loss in a suburban area, the same formula can be used with a correction factor again. So Hata modified his equation to incorporate your suburban area. The path loss was given by L50 dB for suburban area is equal to L50 for urban, which we have calculated earlier. See this formula. Using this, whatever path loss you got, which was for urban, that has to be used, minus 2 times of log fc by 28 the whole square minus 5.4. This was the formula suggested by Hata to find out the path loss for your suburban area. Now, if you have to find out the path loss for rural area, Hata formula was again modified, and this time the formula was given by L50 urban minus 4.78 log FC the whole square plus 18.33 log FC minus 40.94. This was the formula given by Hata to find out the path loss in case of rural area. So you can see one thing which is common to all your formulas, you have to find out what is the urban area path loss. So irrespective of what is the area under consideration, you should always find out the urban area path loss. So when you're writing your code, the first step should be to find what is your urban area path loss. So you will have to find out what is, you have to use all these parameters, find out what is the value for your urban area path loss using Hata. And then depending upon the area under consideration, if it is a suburban area, you can go for this formula. If it is an open rural area, you can go for this formula. Okay, so finding out the urban area path loss becomes a necessity in case of Hata model. Let us look into the code. So we are first considering, you have to take an input from the user, asking him to give what kind of city it is. Is it a small or a medium city, or is it a large city? And then which we use t as the index. And similarly, you take an input from the user, asking enter the type of city again, whether it is urban, suburban, or rural. Okay, these two inputs are taken. The reason, already, to calculate, you have different set of formulas, so you should know what is the area, what is the type of area. Now, the HTE value, enter the height of the transmitting antenna, and the range has to be between 30 to 200 meters. Similarly, find the value for HRE. We'll not find, input the value. We ask the user to input the value, and again the range has to be between 1 to 10 meters. And the frequency of operation we have to provide, the user has to provide, and the range is between 150 to 1500 megahertz. And the distance of separation between the transmitting and receiver antenna has to be given, and it has to be in kilometers. Okay, so these are the few inputs which we are taking. Now, first step, we have to calculate what is the urban path loss using the Hata model. That was the first formula which we saw. Let us come back to it. So we have to first, irrespective of what is the area under consideration, you should always find what is the urban path loss using Hata, because further from there, whether it is suburban or rural, we'll be using the urban area path loss formula. This data is required to compute all the others. So we have to compute the urban area path loss, for which, let us see, this is the formula which we have to use. Now here, the all others are direct substitution apart from AHRE. You have to first find what will be the value for AHRE, for which we know the formula to be used is this. But then there is a dependency. You have to check whether the city under consideration is a small or a medium sized city, or it is a large size city. If it's a small or medium size city, we'll be using this formula. If it is a large size city, we'll again have to consider the frequency, if it is less than 300 or greater than 300. So that is how we'll have to go about with it. Now let us go to the code. So if t is equal to 1, so that is a city, correct? That is the input we took from the user. See, initially when we took the input, we gave t is the value which we are asking the user to give. Is it, what type of a city is it? Is it a small or a medium, or it is a large city? So if it is given, it is equal to 1, indicates it's a small city. small or medium sized city. So the value of CF we know is given by 1.1 into 10 to the, log to the base 10 minus zero point 0.7, correct, into HRE minus 1.566 into log to the base 10 F minus zero point 0.8. Else if, now we are considering what is the frequency. Initially we have to, as told, we have to check for what is the frequency of operation. If it is a city, what is t is equal to 1? T is equal to 1 is a small or a medium size city. And then we again have a consideration, what is the frequency that is to be operated. So for a large city you should have either, for greater than 300, this is the equation we will use. If it is less than 300, we'll be using this. Now if it is a small or a medium sized city, we have only one equation, there is no problem. That is what initially we have done here. Here when t is equal to 1, it is for a small or a medium sized city. We have used this formula directly, no problem. There is no consideration at all. There is no other, there are no priorities here. It is a direct formula. When the user has given t is equal to 1, the program should only execute this line. But if it is not equal to 1, indicating what? It will indicate that the area under consideration is a large city. If it is a large city, there are two possibilities. The frequency can be either greater than 0 or less than, I mean, greater than 300 or less than 300. And we know if it is less than 300, we have this as the formula to calculate the correction factor. CF is the correction factor, okay? So this formula we will have to use, that is 8.29 into log to the base 10 1.54 into HRE into log to the base 10 1.54 into HRE minus 1.1. Else, what is else condition here? If f is less than 300, we use this. So else would be f is greater than 300. We'll use the other formula. That is 3.2 into log to the base 10 11.75 into HRE into log to the base 10 11.75 into HRE minus 4.97. So this is the formula we will be using to compute what is the correction factor. Okay. For large size city, if the frequency is less than 300, we will be using this. If it is greater than 300, we will be using this. Okay, I hope everybody has a clarity. Let me begin from here. Here we took t is equal to 1, indicating it is a small or medium size city. Small or medium size city, so for which we know the correction factor is given by this. Now if it is not, else if, so you are breaking this condition, that is if it is not equal to 1, then we'll come here. So here it is a large size city. Large size city, we know there are two consideration. There are two set of formulae for your correction factor. One is if your FC is greater than 300 megahertz, or if your FC is less than or equal to 300 megahertz. So we are first considering, if your frequency is less than or equal to 300 megahertz, we are going to use this formula. If it is not, then it will straight away use this formula. Okay. I hope you all have understood this. Now, the to find out the path loss using the Hata model, as I told you, we will only have to find the correction factor, that is AHRE. All others have to be just substituted. So we are using the formula to find out the path loss using Hata model, which is given by 69.55 plus 26.16 into log to the base 10 of F minus 13.82 into log to the base 10 of HT minus CF, the correction factor. In our equation, we have written it as A of HRE. So here I have used CF, so I have just replaced it as CF plus 44.9 minus 6.55 into log to the base 10 HTE into log to the base 10 of D. This is what we have found out now. So the first step of calculation is over. Now we have calculated the urban path loss, that is path loss for an urban area using Hata model. Now as we had discussed earlier, again there are two considerations. It can be a suburban area or a rural area. So depending on that, you will again have to compute, correct? So we have taken consideration as u here now. U, if it is a suburban area. So for suburban area, we know we have this as the formula. Suburban area is a formula of L50 urban, which we calculated now, minus 2 times of log FC by 28 the whole square, minus 5.4. Similarly, if it is a rural area, so you will have U is equal to 3 then you will use this formula to find L50 urban minus 4.78 log FC the whole square plus 18.33 log FC minus 40.94. Okay, so let us come back to the code. Now here he has taken an input. Let us consider he is checking if u is equal to 2, which will indicate it is a suburban area. Okay, so we have to use the formula for suburban, which would be L50, which we just calculated here. Okay, we have calculated the L50 value in this step. Okay, this is your urban area path loss using Hata model. Okay, we have just computed that value is to be used here. Okay, that value is to be used here, minus 2 into log to the base 10 f by 28 into, because it is square, so log to the base 10 f by 28 minus 5.4. Now if this condition, if u is not equal to 2, then certainly it has to be equal to 3. Then what is it? It would be a rural area. The area under consideration is a rural area. If it is a rural area, again, L50, we have already found out it is the urban area path loss using Hata model. And then the remaining part of the equation has to be substituted, by which we will find out the value for your rural area path loss using Hata model. Okay. So this will give us the rural area path loss, and this formula will give us the suburban area path loss. Suburban area path loss. I hope everybody has understood this. And then we can go to, go on to plot your graph and display your results. And just a minute. Yeah. So we have found out what is the path loss for the urban area, what is the path loss for the suburban area, and what is the path loss for the rural area. So that is what was expected. And then it's all about displaying what we found out. You can, this part is used to display the plot or the entire range of frequency. So we are again computing this and we are directly plotting it. So that all is not an issue. So the main part is how you have understood how to calculate the Hata model path loss, how to incorporate each of the conditions. Like you will have to check whether it is a small or a medium area. You have to find the correction factor corresponding to it. For a large area, it is again dependent on frequency. So you will have to incorporate that. And further from there, once you have found out the path loss, then you can find out a path loss for the urban area that can be further extended to find a suburban area path loss or a rural area path loss. Okay. So the result would, you can, the input will ask you to give you the value of the city you are considering. You can either give one or two depending on whether it is a small or medium city or a large city. You can also, it will again ask whether it is an urban, rural, or suburban area, and then the antenna height, then the receiving antenna height, and then the frequency and your distance. When you're giving distance, you have to pay attention to a fact that you have to see to that you give the distance in kilometers. Okay. In case if the question is given in terms of meters, kindly ensure that you give in kilometers, and the output would look like this. It First we will be finding the correction factor, followed by the path loss for an urban area, suburban area, and rural area. This is for a small or a medium city. For a large city, similarly, you can find out what would be the corresponding value of your correction factor, your path loss for urban area, path loss for suburban area, path loss for rural area. Okay. I think, and then we can have these graphs. This is a graph for your transmitter antenna height to propagation path loss. I think it is not very clear. Similar to what we saw in Okumura model, you can see as your the height of your transmitter antenna increases, the path loss will get reduced. Okay, and here is again another graph for frequency versus propagation path loss. Okay. So I think once you implement this program in MATLAB, you will be able to see all these plots and all the results by yourself. I hope you all have understood how we go about with, uh, you know, the logic behind coding this and an overall idea of what is the Okumura model. I mean the Hata model. So we'll meet in the next session. We will take up the next model. Okay. So thank you for now. Thank you.